In today's lesson, we continue our work with trigonometric equations, and today we're going to focus our work on functions involving half angles and multiple angles. So sometimes these equations are going to require adjusting solution intervals to fit their given domains. And they're also going to require us to remember our trigonometric identities that we learned in Chapter 5 that you should all have in your flip books. So let's start with equations that involve half angles. So we'd like to solve the equation over the interval from 0 to 2 pi. And notice that we're solving it for not x, but for a half angle x over 2, which means we're going to have to adjust our interval. So very simply, we're talking about the interval from 0 to 2 pi, which means if we divide everything by 2, we change our interval for x over 2 is going to involve everything from 0, including 0 to pi. Well, not too terribly bad on this one. It's kind of like a linear equation. We're going to go ahead and divide everything by 2, giving us the sine of x over 2 equals 1/2. Then we'll go ahead and do our inverse sine. So here's where you need your unit circles at, and you have to find out where is the sine equal to 1/2. Well, it's equal to 1/2 when you're in the first quadrant at pi over 6, and it's also equal to the second quadrant where you are 5 pi over 6. Then we'll go ahead and multiply both sides by 2, giving us one answer of x equals pi over 3. Multiplying by 2 gives us our second angle answer of 5 pi over 3. Both of those falling within the interval from 0 to pi, so thus our solution set will be pi over 3 and 5 pi over 3. In our second example, again, very, very similar. So we're talking about the half angle, x over 2, so that means our interval is going to shrink from 0 to pi. So again, we're going to divide both sides by 2 square root of 3. And we're going to go ahead and rationalize this denominator so it becomes an easier form for us to see. So multiplying both top and bottom by square root of 3, we get 3 square root of 3. And that will be over 6. That becomes the square root of 3 over 2. And then we'll go ahead and do the inverse sine. And remember, the inverse sine simply means you know what the ratio is and you're looking for the angle that gives you that ratio. So again, we're going to go back to our unit circle. And notice that the inverse sine of square root of 3 over 2, well, that's at pi over 3. And it's also at 2 pi over 3. And again, we can multiply both sides by 2. And we get the answer of 2 pi over 3 and 4 pi over 3. Would be our two x's. All right, let's continue now. And we talked about an equation that has multiple angles. So this is where we're going to be using those double angle identities that we learned in Chapter 5. So we're going to, again, solve the equation over the interval from 0 to 2 pi, which means that we're going to be in radians. And notice that our first example says it's the cosine of 2x equals the cosine of x. Well, similar to how the equations that we worked on yesterday, we can't really solve it if it's got two different functions in it. Yesterday, remember how I had tangent of x and secant of x, so we needed to get one of those to be the other. Same thing here. We really don't want to solve this if it's got 2x and x. So we're going to use our identities, and hopefully you remember, or you can look them up in your flip book, we have an identity for the cosine of 2x, and it's 2 cosine squared x minus 1. Again, there's 3 versions of this identity, but we want this version because it's got cosine of x, which is what the other side is. So we're going to start by replacing this cosine of 2x with 2 cosine squared x minus 1. Hopefully you might recognize that this is a quadratic equation, or at least it looks like a quadratic equation because of the presence of the squared. So we're going to go ahead and move that cosine of x to the opposite side, making it negative cosine x. And again, we're going to go ahead and let u equal the cosine of x just like we did yesterday. That gives us 2u squared minus u minus 1 equaling 0, which hopefully you recognize as a factorable quadratic. 2u times u, and then it'll be minus 1 times plus 1. And then by the zero product property, we can set each of these factors equal to 0. 2u plus 1 equals 0, u minus 1 equals 0, which means that u could equal negative 1/2, or u could equal 1. And now we can go ahead and replace our u with our cosine of x. So thus x equals the inverse cosine of negative 1/2. X equals the inverse cosine of 1. So again, we're going to look at our flip book, or our unit circles in this case. We need where the cosine is negative 1/2, which means it's going to be in quadrant 3 and 4. And it is the pi over 3 values of 3 and 4. So here x could equal 2 pi over 3 or 4 pi over 3. And here, where does the cosine equal 1 at? Well, it equals 1 at 0. So thus our answers, and again, we'll put these in set notation, will be 0, 2 pi over 3, and 4 pi over 3. Moving on to example B. Again, notice that we can't really solve an equation that's got one as a sign of just a single x and the other as a sign of a double x. But we're going to be able to use our identities. And if you recall your identity for double angle for sine, it was 2 times the sine of x times the cosine of x. Now, you might be thinking, well, we're bringing in a second angle. And we are, but in this case, we're going to get an equation that we'll be able to work with similar to ones that we did yesterday. So we'll replace sine x of 2x with 2 sine x cosine x. And we're going to solve this by using the factoring in zero product property. So I'm going to take this sine of x, and I'm going to move it from the left to the right and make it negative. Then, hopefully you can recognize, well, I can factor out a sine of x, giving myself 2 cosine of x minus 1. By the zero product property, that means that the sine of x equals 0, or 2 cosine of x minus 1 equals 0. So here, x will equal the inverse sine of 0. Again, you're going to look at your flip books, and you're going to see that that happens at 0, also at pi. Here, cosine of x will equal 1/2, which means x will equal the inverse cosine of 1/2. Again, looking at your unit circles now, that occurs at pi over 3 and at 5 pi over 3. Again, for the unit circles, everything in the first quadrant is just a single pi with that denominator. And here's how I remember to count my way around the unit circle. Vertically, whenever I go from like second to third or from fourth to first, it's always plus 2. I look 2 plus what gives me my denominator of 3? Well, that's 1. So that means for pi over 3's, I'm going to add 1. So that's 2 pi over 3. Down here, I went vertical, so that makes this 4 pi over 3. Add 1, and I turn it to 5 pi over 3. And again, I like radians versus degrees because I don't have to find any reference angles or anything. I just know that it's going to have something with a denominator of 3. So again, writing our solution set, putting the values in numerical order from least to greatest, I get these 4 answers: 0, pi over 3, pi, and 5 pi over 3. And finally, our last examples, again, we're going to be using the double angle identities. And we're going to be doing them just slightly a little bit different in this case. So here we've got 4 sine theta cosine theta equals the square root of 3. Unfortunately, we can't do any factoring, so we're going to have to do something else. So we're going to have to remember that that sine of 2 theta equals 2 sine theta cosine theta, which means that this 4 would equal 2 times 2 sine theta cosine theta, because of course 2 times 2 equals 4. Then we can substitute in 2 sine theta cosine theta. Well, that is the sine of 2 theta. Now, unlike up here, where we wanted to get rid of this cosine of 2x and make it a cosine of x, because we had another cosine of x here. Same thing here. We had a sine x and we had a sine 2x. We want everything to be just a sine of a single angle. Here, we don't have that situation. We can solve this for sine. So we'll go ahead and divide by 2. Tells us that the sine of 2 theta is the square root of 3 over 2. Again, when you're looking to solve for thetas, that means you're going to be using the inverse signs. So looking at your unit circle, where is the sine, the square root of, what angles have a sine of square root of 3 over 2? Well, that happens at pi over 3. And it happens at 2 pi over 3. Which means that theta could equal pi over 6. Theta could equal pi over 3. Now, this we have to do a slight twist to with the double angle. If you remember when we did the half angles, how we divided everything by 2 so we could figure out what 2 theta would be, here, since we're dealing with 2 theta, we're going to have to double everything. Which means that our interval for the answer is actually going to go, for 2x is going to go from 0 to 4 pi, which means that these have to be accounted for going around the circle. So here, our 2 theta equaled pi over 3. Well, if I add pi over 3 plus a rotation of 2 pi, which hopefully you can see, that would equal 7 pi over 3 times by a half. That means that theta could be 7 pi over 6. Here, our original 2 pi over 3 plus, I'm going to go ahead and make 2 pi just be 6 pi over 3 so we get a common denominator. That means that 2 theta could equal 8 pi over 3, and then taking half of that gets the additional angle that theta could be 4 pi over 3. Again, we have to extend because of the fact that 2 theta will go from 0 to 2 pi, or 4 pi, excuse me. So that's our solution set for this problem would become, again, we'll put these in numerical order, pi over 6, pi over 3, 7 pi over 6, and 4 pi over 3. So there's actually 4 answers for this particular question. And our final example, nothing really that we need to do here. This one's very straightforward. It's almost like a linear. So we can go ahead and divide by square root of 2, which gives us cosine of 2 theta equals negative 1 over square root of 2, which you might not recognize yet, but if we rationalize the denominator, now hopefully you recognize it as square root of 2 over 2. So again, our 2 theta will equal the inverse cosine of negative square root of 2 over 2, which means that you're going to go ahead and look it up in your unit circle. That means that 2 theta could equal, cosine's negative in quadrants 2 and 3, so that means it could be 3 pi over 4, or 2 theta could be 5 pi over 4. So again, we'll multiply by 1/2, so theta could be 3 pi over 8. Multiplying by 1/2, theta could equal 5 pi over 8. And since we're talking about 2 theta, whose interval will extend from 0 to 4 pi, therefore we have to take our originals, our 3 pi over 4, and we have to add 2 pi. So in this case, it'll be 8 pi over 4, so that could mean 2 theta could equal 11 pi over 8, which means that theta could equal 11 pi over 16, and the 5 pi over 4 plus 8 pi over 4 gets us 13 pi over 4. Half of that, 13 pi over 8. And I realized I just made a mistake back here. This is actually 11 pi over 4, so that's going to be 11 pi over 8. Let me go back and clean that up a minute. I made the mistake that when I was adding the fractions together, I added the denominators instead of keeping them the same. So, thus our answers for this would be the following set. 3 pi over 8, 5 pi over 8, 11 pi over 8, or 13 pi over 8. Final answer. So that concludes our work with trigonometric equations. If you have any questions, ask. You can go back and watch the video as many times as you need to watch it. And I'll let you get started on your assignment.